So my great pleasure today to introduce Dr. Ray Smith from U.S. Environmental Protection Agency, U.S. EPA. So Dr. Smith received his PhD degree from UMass Amherst, and after a very brief career in the industry, he joined EPA and has been there for about 25 years. His research, as you can see from the title, has a very strong connection with system engineering and environmental problems. I believe it will be of great interest to many of us. He has been a very prolific author, publishing many papers and giving a lot of talks globally. He is particularly influential in many domains, such as plastic issues or exposure issues and so on, that are of great importance to the environment. And he is a fellow of AICHE a few years ago already. So please join me to give Dr. Smith a very warm welcome. And look forward to
Thank you, Dr. Yu. Thank you. I appreciate it. I was actually thinking about a different title that I should have put for here. It should have been Environmental Applications for Systems Engineering, not that the systems engineering are for the environmental applications. But I have to, as a EP employee, start off with a disclaimer that these are just my views and they don't represent those of the EPA. So it's just something we have to start with. So here's what I'm not going to talk about today. I've done a fair amount of work over 25 years, and I just kind of distilled it down into 5 bullet points of I started my career coming out of chemical engineering. I was working on design of chemical processes. And so we developed a tool called GreenScope. It has about 140 indicators, 4 areas. So of course, environment, right? Energy, economics, and efficiency. And the idea there is to put these indicators on a scale so that we know what the, say, worst case is and the best case are. And then every indicator has that sort of scale, and no matter what the process is that we're comparing, we can compare two very different processes because we have that set scale. If you didn't have that set scale, you do a lot of comparisons, and it's very tough to make comparisons in that way. So other work I've done on industrial ecology, and what I wanted to bring up was the fact that we were looking at genetic algorithms. So I know a lot of people here are going to be into different methods doing calculations. So I thought I'd bring up that aspect. Worked on supply chain design, but also life cycle assessment. So we were doing life cycle assessment on fuels. So comparing ethanol to an additive called MTBE, which it was good for the air, but it wasn't good to cause water problems. And so some life cycle work on that. Decision making. The idea here is that can we talk about exchanging one thing for another? And what we developed was what we call marginal rate of substitution. So much of one thing can be traded for so much of another. Once you develop those relationships, then you're able to add things on a single scale, and that's what that work, in a nutshell. I mean, these are all extended pieces of work, but that gives you on a nutshell what that is. And then this work on environmental releases, I'll talk a fair amount about that today, but some of our work is using machine learning. And I know that there are people here that are very interested in machine learning and AI. So also, I just wanted to bring up systems analysis, and that I think we should be considering all these aspects of the system, from designing them to constructing them, the operation, and then its end of life. So whether it's the system itself, like the infrastructure, or whether you're into production of some product, you're making something and using it, there's also an end of life to products, right? But also there's a design phase where we design them. So can we say more about the environmental aspects, both resources being used? This is going to be a theme through this talk today, is what are the resource use? How much of different resources are being used, and then what are the releases of the environment? So emissions mostly, and then some on discharges and solid waste. So outline of what I am going to talk about. Three things: predicting those releases and so forth. some work on above ground storage tanks and how climate change and extreme events can affect them. And then talking about recent work on recycling plastics as well. So first one, predicting chemical process releases. Here is a diagram of a thermochemical process for cellulosic ethanol. And you're not supposed to be able to read this. It's just that, yeah, we have a process that we, have defined streams, processes within it, that we're considering all these aspects like cooling and wastewater and steam and power generation, etc., right? And we were doing this similarly for a separate process, biochemical. Again, looking at the different aspects, we have the different flows, etc. So what are the inputs going into the cellulosic ethanol process? So there's essentially two groups of columns, right? So the inputs listed, and then the thermo and biochemical. And so what you can see, the biochemical in total has a lot more, right? So there's a lot more mass going in, a lot more makeup water, and a lot more biomass going in, right? So in terms of efficiency of just mass, it's not very efficient. There are certain inputs that are particular to the thermo process, right? Catalysts and these few here. But otherwise, everything is majority of this biochemical process using a lot more inputs. So why do I bring this up is that each of these inputs should have a stream coming in, right? And describing what those processes are upstream if you want to look at the whole system, right? But then we looked at, okay, so what are the emissions coming off of both of these processes? And here it's really a mixed story, I guess, between the two. That some places the thermo is producing greater amounts, and some places the biochemical one. So I don't have a story to say that, oh, this one is considerably better than the other, but just that we need to consider all these aspects if we're going to look at all the environmental effects that these systems could have. And actually, there were a lot more that I couldn't include in here. So when we wrote a paper on this, we have supplementary information that has a lot more emissions than this. So how did we do those calculations and what's available? So it was just a spreadsheet. Here it was for the cooling tower. And so, how much cooling demand do we have? We had to pick certain temperatures and make certain assumptions. But then we could say, okay, well, here's what you're going to have in terms of resources going in, because they do use chemicals in the cooling towers, okay? But also, what are the releases from those? What are the emissions going to be? Well, the reason I brought that up is it's not just cooling towers, it's boilers, right? You're going to need some kind of energy in your systems. There are going to be fugitive emissions for all these. In these bioprocesses, you're going to be using forklifts and trucks. And then there's storage of chemicals, both as inputs and the products, right? So all these things are available. And essentially what I'm doing is pointing to this paper that we published, and all these Excel, little, short spreadsheet. But what if someone were interested, they could take each one and import it essentially into their work. And I think it would be valuable in getting a more complete picture of what's needed in terms of resource use, but also releases to the environment. So that's the big idea in doing this. And it's going to be running through some of the work that I'm going to present today. So in this last aspect here, storage, I'm obviously going to go into some more detail here because this next part is above ground storage tanks, right? How climate change and extreme events can affect them. So our gasoline supply chain looks something like this, where we're mixing ethanol with crude oil-based mixing stream, blending stock. And really they meet at this fuel terminal. And so fuel terminals, let me see if I can remember the statistics. There are about 1,450 terminals in the United States. I want to say a bit of less than 1 billion barrels of capacity, like 900 something. And the average is 750,000 million barrels of capacity at each fuel terminal. So they're on average 19 tanks. So I wanted to give you an idea of what the size is and how many of these processes there are. So this aspect leads to, okay, so if we have all these fuel terminals, how are we storing these fuels? And you might be using this fixed roof type tank. So there's a reference down here, I don't know if you can see it, says AP42. This is an EPA document. Describes these tanks of different sorts. So when you're storing a chemical in here, you can see the vents in there, all right? When the temperature increases in the tank, the vapor pressure increases and the amount of venting increases. If you pump something in, it also fills up more of the tank and it pushes the vapors out as well. And there's, of course, there's little leaks as well, right? Well, if the vapor pressure is high enough, that requires some sort of control technology. You can't just have this tank with these openings letting the chemicals out. So what some people do is they put a floating roof on top of the stored material, so like a gasoline. So this is like sitting right on the gasoline, right? This roof here. And the roof moves up and down with the material, right? So you pump something in, the roof moves up, you pull the material out, and the roof sinks. Well, when the roof sinks, you can imagine that the sides of these walls are still going to have liquid on them, right? Because you dropped the roof, this floating roof down. And so that material evaporates. You have breathing losses. So what happens is it gets hot during the day and then cool at night. And so the difference in temperature leads to emissions. And then finally, all these deck fittings, you can see all these items in here, and there's rim seals along the edges. All these things can have leaks of emissions as well. So it's not going to look like a real tank, but what real tanks deal with is all of these emissions coming out of here, right? And they could be looking at leaks coming out of the tank. So all these tanks have different age, they have different maintenance, they have different materials inside them, they're in a different location, right, which has different weather, right, different climates, right? But then there's other things on the outside affecting. You could have a heat wave, a lot of sunlight, right, and heat. You could have storms and lightning strikes affecting the tank. You could have a flood. You could actually have things like hit the tank, right? Physical damage. You could have waves of water hitting, and you can have winds. So you can imagine if winds come inside this upper part of above the roof, that they clear out whatever emissions are there and create a larger driving force for more emissions, right? So thinking about all these things, I just want to quickly go over, I don't know that I need to convince anyone, but that based on, this is from NOAA, so the National Oceanic and Atmospheric Administration. They did an average from 1901 to 2000, picked an average, and here you can see the anomalies from that, and it's increasing. In fact, if you have the last few years, they're also up here, right? So temperatures are increasing. It looks like it's a degree Celsius above what the average was in the 1900s, right? But you may not be aware that sometimes there's large variations in wind speed as well. So this is for a place in South Dakota. Sisseton is on the border of North Dakota, and it's also on the border of Minnesota, just to give you some idea where it is. And so, yeah, there's this average around 12.5 miles per hour. And you can see that every April, the winds might vary a bit, maybe 10%. And then suddenly here, a couple of years ago, it was 28% higher. If I'm the winds were 28% higher, right? So this is for the month of the average. was actually, there were a lot of periods of like 65 plus mile per hour winds, okay? And they weren't short periods. It was like a few days at a time. So both these temperatures and these winds are important because those are the things I'm going to show you in the calculations here. And that we have a model to describe what the emissions are based on temperatures and winds. Now this is the percent above the baseline. And then the y-axis is the percent increase above the baseline emissions. So there's specifics. I had to pick a specific tank size. I had to pick an actual fuel and describe what the gasoline looks like, all the components, how much per day gets used, and well, location, and so forth. Lots of details, right? There's specific, for this location, there's specific temperatures and wind speeds that are average, all right? So what this includes is these breathing, working losses, and standing emissions. And you can see that they increased. I see that the VOCs increased by about 63% here. And while that was increasing 63%, the aromatic emissions of aromatic chemicals were increasing by 84%. So one of the reasons I would point out something like that is often aromatics are more toxic. There can be a lot of problems with aromatic chemicals. So we might be interested in a local community to know, hey, we could have periods where there's significantly increased emissions of these chemicals, right? Now, what happens when there's lack of maintenance? So that's some of the rim seals are just primary instead of also having a secondary working rim seal, or some of the deck fittings aren't gasketed properly. If the shell of the tank gets aged and rusted, that adds to emissions as well. And what happens is just at the baseline, emissions jump to 125%. Above the baseline. So this maintenance is a really important thing. The other thing is that the slopes increase for when we have higher temperatures and higher winds, right? And so we're seeing much higher emissions based on the fact that there's a lack of maintenance. So same case study, one more graph on it. So these are the original ones that I showed being at the bottom of the last figure. But now if we have both increased wind and temperatures, how the emissions are increasing. And so there's a dramatic increase just from these calculations here if both the wind and the temperature are much higher. So it's not often, but I have seen some increases in temperature that are pretty extreme. The Pacific Northwest has had some heat waves just in the last few years that were really pretty darn extreme. They're talking about hundreds, temperatures over 100 Fahrenheit, and that's not something that they commonly see, on average. So some of their temperatures could be really way above, but also I think higher winds are much more common, right? But the combination could occur, and we could see dramatically increased emissions. So this is just a summary slide about this work. So, all these things can lead to, there are effects that I'm not talking about here, like the lightning strikes can lead to fires. So you can still have fires. Aspects of the roof flooding. So if you have enough rain, the roof actually fills up with water. I mean, there's normally a drain on it, right? But the drain can't handle the rate that things are raining. And then the water could actually get into the tank instead of what's needed. So there are a lot of aspects about these tanks. So again, we have a publication on this if you're interested in more details. So finally, we're going to talk about recycling plastics. So this is ongoing work. So perhaps we're all aware that generation of plastics is increasing. In the U.S., in this time period, it was 2011 to 2021, and the COVID year of 2020 was in there. So I think maybe manufacturing was really down during part of this period. And so that's why you might see the annual manufacturing growth was actually negative for that period. But at that same time, U.S. plastics was increasing. I'm sure it's still increasing. Since say the 50s, the amount of plastic produced is huge. So that M stands for million metric tons or megatons. So this is a lot of plastic that the world is generating. So things have gone from 2 megatons per year in the 50s to in a recent year, 2019, 5 years ago now, actually, 368. And there's some talk about quadrupling again by 2050. What are some of the effects? Well, some of this is related to economics and just the fact that our beaches, places that you would see litter, plastic pollution, have value. And so we could expect that these jobs, these recreational value, et cetera, could diminish if there's too much litter, especially plastic litter. Recycling does offer some opportunities in terms of jobs and wages and tax revenue. And here you can see the total in terms of recycling, but also what the aspect of plastics is provided according to this. It was a 2016 report, actually. So some ecological effects. I talk about some pollution and why we should be somewhat concerned about all this plastic. So plastic entangles fauna. It could smother aspects. The rafting of species and pathogens is not something I thought about, but actually something could ride on a piece of plastic and go from place to place. So you could actually have something become invasive in a new location because of that. But also just the ingestion of fragments, so little bits of micro or nanoplastic. So they've been found in various fauna, right? All sorts of types. And the turtles are particularly vulnerable because they can't regurgitate. We've seen it in small zooplankton. So about the research that I saw said that 3 to 6% of the zooplankton that they found had microplastics in them. The other fish are eating a lot of zooplankton. So they're getting a lot of exposure to these microplastics. Also, the microplastics damage corals. So corals are valuable for their diversity, right? A lot of life depends on them. And just plastics in general have a negative effect that disease arises in coral because of plastics. Now, there are other things that are affecting coral, right? Heat, acidity, things like that. Just a little detail, I don't know if we can read that low, but microfibers are denser than seawater, so they're expected to remain at the bottom of the water bodies for many decades. So you can imagine that these microfibers are going to be around for a long, long time. What about our intake of microplastics? Well, according to this study, around 39,000 to 121,000 particles per year is what we're taking in. They added that if you're drinking bottled water, that adds another 90,000 microplastic particles a year, but only 4,000 for tap water. I'm sometimes still drinking water from plastic bottles, but I'm thinking about really reducing the amount that I do that.
That's what we have right now.
I know. Yeah, but I'm thinking about ways of not doing so much plastic. So, so mice in this study here, the mice were fed different sized microplastics, and just over 4 weeks, and they found the livers, the kidneys, and the guts were accumulating 1 in 1,000, so a milligram per gram of microplastics in them. So while the liver weights were decreasing, the amount of food that the mice were taking in increased. So they were eating more, right? But energy and lipid metabolism were impaired, and there was inflammation and oxidative stress seen. The other thing that happens in these studies is that the smaller particles generally accumulate more. How about PVC bottles or plastic? Well, there's phthalates that are used. So how about the chemicals that are in the plastics? So the FDA was petitioned by the NGOs, non-government organization. So NGOs wanted to prohibit the food contact with these eight phthalates, right? So here's the group of phthalates called diisononyl phthalate category. And so this group was added actually to what's called TRI, toxic release inventory. And so the EPA does this when there's a substantial amount of a material and it's toxic, right? So it's a sign when the EPA decides to add a chemical or group to its toxic release inventory listing. So how about our poly and perfluorinated polymers? So they're used in a lot of food contact, right, for linings. One study found that fast food paperboard, like maybe something that your French fries might come in contact with, that 20% of those contain fluorine, whereas the wrapper that wrapped your sandwich was about 46% contained fluorine. So just the beginning of a month ago, February, the FDA declared that these grease-proof agents that are PFAS are no longer being sold in the U.S. market. So why do you have to, why do you have to bring that up? Is because they are being sold in the U.S. market, right? So, yeah, we're coming into contact with these PFAS materials often. The other thing about these chemicals is that, and this is about textile products, this quote, but it's virtually impossible for consumers to make informed purchasing decisions for recyclers and to recycle them safely. What I would say is the same thing goes for packaging. So we don't know what the chemicals are. If someone has added any chemicals to this bottle, I don't know what they've added, right? None of us do. So, I mean, this is an issue. I'd like to tell you all about the releases. I can tell you about some of the releases to the environment, but I can't tell you about the things I don't know about, right? So it's sort of an incomplete story. We're learning more and more, but doing the best we can with what we know. So the EPA has a national recycling strategy, and in this aspect of it, there are three objectives: to reduce contamination, increasing efficiency, and improving markets. So their approach is to understand these system flows and barriers to increase recycling, to profile the processes and impacts. And then what I did is I started going by plastics and started saying, what can I say about different plastics? So I started with PET, which is otherwise number one. You can see it on the bottom of something. And there's a fair amount of information available on PET. What does the system look like? Well, there's different ways that we collect PET or other packaging, right? So we have curbside collection systems. We have some states have bottle take-back, right, systems. And sometimes you have drop-off locations, right, where you drop something off. Well, a lot of these are mixed plastics, right? So they have to go to some sort of separation. So the material recovery facility is a MRF. So we have to do some sort of separation of those materials, and PET bales are one of the separated products that come out of there. But those need to be improved. The PET bale is not ready to be made into products. It has to be cleaned up. And so there's a step called reclaiming that creates a flake that is usable in these systems to make new recycled products. And this could be incorporating just a certain amount of recycled PET in a new product. So this is what the material flow looks like for PET resin. The numbers here are in millions of pounds. So one way to look at this is to start with the blue material. This is what's collected. All right, so we're collecting bottles in the US. So about 2/3 of the bottles are collected curbside, another third are collected in deposit return systems. We can get the total collected and then the total that go to what we call reclaiming, right? Some gets exported, right? But it gets mixed here with some of this yellow. So there's sheet and film. These are essentially thermoforms. So this is like the clamshell type stuff that you might see in a grocery store. Some of this material comes in and gets mixed in, right? It's inside the bale, like when you have the PET bales of bottles. Well, there's going to be some of that material in there, right? And so it's just going to end up included in this reclaimed material. Now, the material that doesn't get collected is going to go for disposal. So along with bottles, other bottles that aren't collected, there's a large amount of disposal occurring. And then a small percentage, about 2.6% of that, I'm assuming, I made a calculation to determine how much is mismanaged, all right? Yes, the problem I think here is that it's 183 million pounds of mismanaged plastic PET in the U.S. every year. So now it is an assumption, but that's a large amount of PET that's just out in our environment every year. This reclaimed material, about a third of it here is just a residue that's not being used, but then about 2/3 of it is going into flake. Some of imported flake combines, and certain products are made from that. So a lot of fiber, some food and beverage bottles, and other non-food bottles, and strapping, and sheet and film, and other products. So what do material recovery facilities look like? I don't know if any of you have had an opportunity to tour one. Some communities will let you just tour the MRF, the material recovery facility. So there's these conveyor belts. This stuff just is flying really fast by. And if there are people doing manual work, they're pulling items off. You'll see them working really quickly. So these conveyor belts are moving very quickly, and there are these images being taken at a certain point so that, when it gets to the end of the conveyor belt, a puff of air can shoot the material over this wall, okay? And so it does a separation. So that some material is pushed over the wall and some just falls off, right? So these are moving very fast. So that's one method to do separations. I've actually seen robots as well. So it's just an arm that picks something up and puts it in, say, 5 different bins. So, but these separations are, and this is just a term we use in say, distillation, the sloppy split. So it's not really a clean, perfect split that's occurring, right? Where we just have a certain material now that we've done that separation. And so the streams that we're going to find are not going to be very near perfect. So I created a spreadsheet just to easily look at, okay, if we have these streams coming in the rows, like the newspaper, bagged newspaper, corrugated cardboard coming in, what percent goes to these different columns? And the columns are essentially products coming out of the MRF. So, yeah, the material comes in, and the bagged newspaper is going to 3 different major streams here, right? Rejects, fiber, rejects, and then this stream of mixed paper. Just as an example. So what happens if we want to look at PET bales? Well, the PET bottles coming in, 89% of them are going to the PET bale. HDPE, high density polyethylene, is also coming into this bale. This is non-bottle PET. 6.8% of what's coming through actually gets into the PET bale. So this PET bale is essentially 95.8, 96% of PET items, all right? But 6.1% of those items are dirt and water residue that's on them. And another 11.7% of them are high-density polyethylene, like a label or an adhesive, or the cap is another material, right? So the PET bale is really just 78% PET. So this is supposed to be a great example of recycling in the U.S., And it ends up that 78% of that bale is actually just PET, which is, the product that you're planning to use. So what do the next step? I said that reclaimers have to improve the purity of that bale. They basically open up the bales, sort the materials again. Finally, they grind the plastic materials, wash it, and then density is a sink float tank. Essentially does a lot of the separation. So some of the PET sinks, right? And the polyolefin, or like HDPE, the polyethylene materials, polypropylene are floating, right? So they can do that sort of separation, then do these drying and sifting steps. So say a 97% reclaiming efficiency, and now 75.7% of that original PET bale is what we have left to work with. If you remember when I was showing you the material flow analysis earlier with all the colors showing the flows of materials, I said that about 2/3 was going to flake, right? About another third was going to residue. So it looks like we have about 10% leeway here to try and improve the system, right? Improve the efficiency of what we're doing there. And that's before we do things like improve the design. So I was talking about design. Do you remember, well, some people might remember that 2-liter bottles used to have a black base on them, and it was a different material. And now they're making the whole bottle out of PET. I don't know if you noticed. The cap still has to be something like polypropylene. They need the material properties of that cap. So they haven't figured a way to make that out of polypropylene yet. But so the cap is still another material, and then there's a label and an adhesive on these bottles. There are still places where they can improve the system and make something that's just PET. So the last slide on plastics is that I think the first 6 rows are resource use. So this is per ton going into the MRF and per ton going into reclaimers. One big thing is that the reclaimer per ton are using a lot more electricity, but there are a lot more tons going through a MRF. Okay? Diesel use about the same. Natural gas is higher in the MRF, and using some chemicals and more water, right, at the reclaimers. This is about the amount of wastewater that's coming out of these processes. You can see a lot more from the reclaimers. That the diesel storage, I was talking about storage emissions earlier. So there's a per ton of feed, how many kilograms are coming off in terms of diesel emissions. And then what are the greenhouse gases? And again, this is per ton of feed. And you can see that they're much higher for the reclaimers, even though the volume going through here is a lot lower. But there's detailed supporting info with a lot more emissions listed. I mean, there's many more included in the details of this. So essentially, hopefully that gives you the perspective I was trying to get to you, is about these. Can we look at all these inputs and outputs for these supply chains, these processes? So a more complete system would hopefully be a better analyzed system and give you the right results. You know, when you're doing some sort of systems analysis, if you don't have the system described correctly, I think your results could be incomplete or not quite right. Are we accounting for all the chemicals and releases as much as we can, right? And that includes things like emissions, the discharges of water, the system flows, and then the solid waste. So if you can, apply additional impact categories. So I know there's a lot of emphasis on greenhouse gases and climate change effects, but yeah, if you can include other aspects like toxicity or other impacts, it would really benefit, I think, your system analysis. So I see that it's about time to start. We could do some Q&A if you have any questions. And here's my contact information. So I'd be happy to receive an email from you if you have anything you want to talk about. And thanks for your attention.
Are there any questions for Raisa?
Thanks so much for being with us today. I have two questions. When there are different types of related plastics, when municipalities only accept certain types of plastics and not others, how does that kind of come into play with regard to the sorting process?
Right.
And kind of yield?
Yeah, there's a lot of interesting things going on there that, maybe I should repeat the question. When communities accept or don't accept certain plastics, how does that affect the separations? Okay. One thing is the value of some of these plastics is fairly high. So in places that have take back, this bottle return programs, states that have that, the MRFs are getting a less economic stream. So they really like the aluminum, right? And some of these plastic streams are also really of value. So the MRF really doesn't have the same economics, right, to operate without those streams. So it's interesting how a choice to do something that is positive, like returning bottles, right, having a system to return bottles, can lead to the MRF struggling. So you might have to have another way of financing those MRFs, all right? But if you are taking materials out of the MRF input, then it could be easier to do those separations. Yeah, and I have not analyzed what that might look like. Like I have that spreadsheet where I was saying if these are the inputs, what are the outputs, in terms of the columns. And I haven't done that sort of analysis to say, well, if you have a different feed stream, what does the MRF look like in detail? Yeah.
In terms of the intake analysis around kind of end products from incineration or from manufacturing of plastics, what kind of process goes into determining what those chemicals are?
So if you're incinerating, or what was there another process?
Oh, so one of your earlier slides at the start of the presentation showed kind of the input chemicals, but then also the output chemicals or the byproducts.
Mm-hmm.
I was just kind of curious, are there certain types of sensors or other kind of analytical tools that are being utilized for that analysis?
That's a good question. I don't think I know the answer. I do appreciate that sensors are getting better and better, and so we're able to pick up a lot more of what's occurring, but I don't have the data on it. What I would like to know from the input side is when someone is making a piece of packaging for us and it's in our food, being used for food, what are the chemicals that they're putting in there? Because then not only would I put it in my research, but I'd make my personal decisions about it as well, right? But yeah, I could improve my research if I knew what those inputs were, right? So yeah, it would be a benefit to know that. I'm sorry I don't have more detail for you. Yeah. Yes?
Do you have trouble getting data from industry?
Mm-hmm. Yeah, I don't. I have other reports and things like that. That's where I get my data. So I haven't. Now the recycler, like the MRF, I showed those pictures because I was able to take a tour, and they were like, "Yeah, go ahead, take pictures, and go share it." And they were willing to email with me and tell me about their, say, energy use and their, things like that, electricity use, etc. So they are willing to share, but a lot of the rest, not that I know of. A lot of it, yeah.
And I'm just curious, where are you working? Washington?
I work in Cincinnati. I'm sorry, I didn't say that. Yeah. So before there was an EPA, Cincinnati was a water office, and they put them all these air office, water office, put it all together and formed the EPA. So yeah, that's why Cincinnati is now a research location. So.
Are there any other questions?
Everything's clear?
I'm just going to check the Zoom real quick to make sure. It doesn't look like there's any questions in the in the chat. So with that, can we give another round of applause to